So welcome back, everybody. It's a pleasure to introduce Susanna Zimmerman with her second lecture on variation transformations and Cremona group.
Thanks for the introduction. Okay, so I'm going to do a short recap from yesterday. So, right, so we have a goal. We have UP2 over some perfect field. And what we want is to embed it into the group weight. Let's say G. I'm going to write it with the name I'm using later. So here, Mori of P2. This is the group weight of directional maps. Between the beta surfaces and conic bundles. Well, we can have from the beta surfaces to the beta surfaces, conic bundles to conic bundles, or from the beta surfaces to conic bundles. Okay, and then we're going to construct a lot of morphisms to Z2 that we can restrict to our Cremona group and get something surjective here. So this is the broad aim of the lecture. And yesterday I was in the course of introducing this group, everyone who lives in this group. So, okay, let me go back to the beta surface and conic bundles. So, okay. I'm going to do a short recap of these. So the beta surfaces here and the conic bundles here are outcomes of the MMP. Okay, so the MMP for surfaces. Or perfect fields. And the MMP for surfaces over algebraically closed fields is just contracting -1 curves. Curves that are isomorphic to P1 and have self-intersection -1. Okay, so there's a theorem that says if we have a curve that is isomorphic to P1 and it has self-intersection -1 in the surface, then we can contract it onto a point, and that point is going to be a smooth point of the next surface. And now the version over perfect fields is exactly this, but equivariant with respect to the action of the Galois group. So we have orbits. Of -1 curves. So here, those are, let's say, these are n curves. And each of them is isomorphic to P1 over the algebraic closure, and each of them has a self-intersection -1. So this means that, okay, and then we can contract into, so we contract these orbits, but so in order to stay within our setting of things that are defined over K, respectively equivariant with respect to this group action, we need to contract these curves all simultaneously, and that's only possible if they're pairwise joint. Now, maybe an example that I did yesterday. So I have 2 points that are complex conjugate, okay, exchanged by the Galois group of C over R, if you want to, or of Q bar over Q. And they're sitting in P2. And we blow up these 2 points. We get 2 divisors, E1 and 2, E1 I0, E1 minus I0, and well, the strict transform of the line that passes through them. And those are -1 curves. And we can contract them simultaneously. But now, so we can also see these as E1 plus E2. So this is one curve. This is the exceptional divisor of so okay, this way I'm mixing C and R, but this is just a geometric picture. So okay, if I this is the picture over C. Now if I have the picture over R, I'm blowing up Z equal to x squared plus y squared equal to 0. Okay. And then I have, let's say this is a point we vaguely see, and then we have a curve here, E. And E, so E over K bar is numerically equivalent to E I0 plus E I minus E0. Okay, but we could also say that each of the components is a P1, and the union is defined over our field. So E is a P1, but over H naught of E O of E. So since E is not integral, it has 2 components. This is C. Okay, this is P1 over C. So here I could also say, so we contract curves curves E that are isomorphic to P1 of H1 E of E, and E squared is negative. So here is E squared is the sum of these 2 divisors squared. And each of them has square -1. They don't intersect, so this is -2. It's not a -1 curve. It's a minus. It's also not what you think is a -2 curve, because in the classical setting, -2 curves, we contract them onto singular points. So, okay, what we called them was just exceptional, the classical name was the exceptional curves of the first kind. In order to avoid issues. Okay. So, and this means, so we can contract them. There exists a contraction from our surface x to y. Let's say f, such that f contracts E onto a point. And that point has exactly the degree of the point is exactly minus the self-intersection of E. Because here we blow up a point of degree 2, and we get -2. And, well, this is a blow up, so F is the blow up of X. Okay, and just to sort of go full circle, this is the same as saying, so E squared is negative, and its intersection against the canonical is negative. Okay, so here we go full circle for the classical MMP. Okay. And all right, so here Kx is H naught of E O of E. So if E has 2 components, that means this is a space of dimension 2, and we have 2 points. If E has 3 components, this is a space of dimension 3, and we have 3 points. Maybe just a very quick idea of, so yesterday at the beginning I mentioned that one of the interests of looking at surfaces over non-closed fields is that they may appear as generic fibers of contractions of fiber type. And if you have a birational map of a generic fiber, that gives you a birational map of your space that is related to the birational map of the generic fiber. And so for instance, if I have a contraction of fiber type, and then generic fiber is X over the function field of Y, then let's say this is a surface. And we have in it a point, okay? And the point is of degree, I don't know, n. So sort of what you imagine is we have, this is x, k of y, we have x of y, and this sort of represents an open subset of fibers. And we have a point here with n components. And what this represents is a curve in X that is an n-to-1 cover of a curve in the base. Okay, so this n-to-1 cover, a priori, it could be n-disjoint curves, or it could be an irreducible curve. So this is not entirely clear. Okay. So this is geometrically what you want to imagine if your motivation is more of a higher dimensional type. And then so intuitively, when you blow up this point X in the generic fiber, intuitively what you do is you blow up this n-to-1 cover curve inside X. I say blow up because it might just be a birational contraction onto that n-to-1, onto that curve. Okay, so this is the idea. So. Yes. I'm thinking, no, because this is a point, because x is a point. And so if... So yeah, x over y is a vibration. Y might be of any dimension, we don't know. But a point in x is going to correspond to a curve in x. So in that sense, for instance, if you have a surface and you have a rational point, this corresponds to a rational curve. No, this corresponds to a curve, a transversal curve in your variety. Okay. Yes. And in that case, if y is one-dimensional, you have a section. So this would correspond. Is it clear what I... Okay. Okay, so if I blow up these points, what I do is I make the points into curves, and then I get... And you just sort of extend. You get, did I point? Yeah, maybe I'm thinking in a specific codimension. Yeah, so I get a subvariety. These correspond to subvarieties in my, curly x. And then you get a contraction up to maybe birational, a bit of modification or small modification. You get a birational contraction that contracts these subvarieties onto these curves. Okay. So this is what you can imagine for a general motivation. Okay. Okay. So now, what are the, well, we have outcomes of the RLP, and those were, so we had clean F, or we had minus K is ample, and the picker rank is 1. Or we have, so this is a variety X, we have a conic bundle structure. With a relative picker rank 1. So, okay. And if our space is rationally connected, or is well, it's over the algebraic closure, it's rational, then only these two outcomes are possible. So we are interested only in these. So happen K bar is rational. I don't know why these happen. And we can put them together into one single definition, and that's the definition of a Morey fiber space. So a Morey fiber space, or Morey fibration, here the naming depends a bit. Space depends a bit on the people. Is a morphism from X to B, the dimension of these at most one. So again, okay, this is a surface, right? Very smooth. One, and that has connected fibers. And the anti-canonical is relatively ample. So it will be, and the relative peak rank is 1. So this means that the anti-canonical is ample on all the fibers, which is, if B is a point, we get X del pezzo. And if B is a curve, we get that all the fibers are conics, plane conics, and then we get a conic bundle. The word bundle is a bit misleading because it's in general not a bundle. It might have singular fibers. Okay. An example of this is the following. So, an example. Right, so, okay, we take our tooled points in P2 and the line through it. Okay, we blow up these points. I'm drawing the geometric picture, okay? So these are 2 -1 curves, and then the line becomes a -1 curve as well. And we can contract -1 curves that are invariant. So here the Galois group exchanges these 2 points, so it preserves the line through these 2 points. So we can contract calmly this line. So this is so maybe I will put the Galois action in yellow. So where are we now? We look at this pencil of lines with these 2 points. They are exchanged by the Galois action. They are pencil of lines here that are exchanged, and they descend to rulings that are exchanged. So here we have a form of P1 cross P1 with a Galois action that exchanges the 2 factors. And in fact, this is corresponds to a quadric surface in P3 that is given by x squared plus y squared equal to wz. So here, this is a priori so this is a del pezzo surface. Over C, it is a conic vibration, so it would belong to this group here. But over R, it belongs to this group here. And now we take 2 conjugate points in here that are not on the same geometric ruling, okay? And we blow them up, and we get following picture. So this was a de Betzel surface of degree 8 because it's a quadric surface, or P1 cross P1. We blow up 2 points, we get a de Betzel surface of degree 6. And it carries a conic vibration, and that's the 1-1 curves passing through these points. Okay? They give us a vibration up here. It's so we can see it if we look at these blue points in P1 cross P1 in P2. Those blue lines actually are conics passing through these points. Okay. And now what does the Galois group do? So I'm blowing up 2 Galois conjugate points. So the Galois action lifts to the surface. And what it does is exchange these 2 red lines, but also these 2 fibers. So we have a conic bundle with 2 singular fibers, but these singular fibers, we cannot contract them equivariantly. So they're irreducible over R. So this is a Moivre fiber space. Okay? It is a conic bundle, but it's not a bundle in the topological sense. It has singular fibers. So and if you want, you can, so if you want to go without the Galois action, you look at this surface as a quadric surface in P3, and then you can pick these points to be W Z square plus y square equal to 0. Okay, these are, so we get 2 points that we get by intersecting this quadric with a line. The line intersects our quadric transversely. So this is just obtained as blowing up P3 in the line and then restricting to the quadric. And what we do is, so we have our quadric, our 2 points are here, and then this is we have a, with these points, we have a vibration, and then we have some irreducible, no, the picture, sorry, the topological picture is better. We have our points, we have our vibration, and then here we have degenerate quadrics. And we blow up these points, and then we get these degenerate quadrics. Okay, so this is the topological picture. Okay. So Moivre fiber spaces in dimension 2 over K bar, they're easy. There's P2, they're Hirzebruch surfaces. That's it. Moivre fiber, let's say rational tool, and here it's above surfaces. So these are conic vibrations with a unique section of self-intersection, minus n. And then over R, there is a classification of these minimal surfaces as well by Comisati. I hope I have the right number of like M's, S's, and T's, please, everyone. I think it's from 1921 or 1920s, let's say. So that says the Mori fiber spaces, rational Mori fiber spaces over R are P2. They're Hezebo surfaces. They are this quadric surface. And this conic vibration, let's say, and so the law, let's say this is Q of Q in S. And that's it. Those are the only ones. And then, so from this, you can show the following theorem that so X smooth projective surface over R, and let's say over C it is rational, then all right. So then X is rational over R if and only if its set of real points is not empty and connected. So one side is easy, this one, because blow-ups of points do not change the fact whether do not change this condition. Okay, it doesn't change the topology of it changes the topology of the real points, but it doesn't change the fact whether it's connected or not. But this direction is not easy, and you can use the classification for it. Thank you. Okay, so we have our minimal models, we have our Mori fiber spaces, and now we want to know birational maps between them. So, and so a Sarkisov link is a birational map between Mori fiber spaces. That is very simple, like the simplest type of birational map between Mori fiber spaces. So let's go maybe to to algebraically closed fields. We have P2. And the easiest thing we can do, apart from an automorphism, is blow up a point, right? And we get to the first Hirzebruch surface. So this is a circuit of link. Then we have Hirzebruch surfaces. So starting from a Hirzebruch surface, we can do two simple things. We can contract the -1 curve, or we can blow up a point. And the two fibers become -1 curves. So the fiber becomes a -1 curve. We have the exceptional divisor. And we can contract the strict transform of the fiber. And this is the easiest thing we can do over P1. That's also a circuit of link. And that's basically all the circuits of links over K-bar that exist. So we have blow up. We have this one, and then we have elementary transformations between conic bundles. So we blow up a point, and we contract the strict transform of the fiber containing the point. Maybe I'll put it in color. So this is the pointer blowing up with the exceptional divisor, and then we contract the fiber. In yellow, I put the fiber, and we contract. So this way we get to control exactly who appears in this way. So what is so let me give you an example to show like what is the more or less good part of it. So we have maybe what is the so we look at the map from A2 to A2. We send xy onto x p of y, and p is some polynomial of large degree. Okay. Then this gives us, so this preserves the vibration y constant. Okay, this gives us a birational map from P1 cross P1 to itself. Okay. And if we want to resolve this map by blow-ups, we have to blow up at least d many points, and we'll get a surface that we have no control over. It can have it will probably have infinitely -1 curves. We don't know anything about the geometry. But what we can also do is just blow up one point, contract the fiber, blow up the next point, contract the fiber. And this way, we will only do elementary transformations between conic bundles, and we will have control over every single surface that appears in this sort of decomposition. So then, so we blow up a point. We contract the fiber. We will get to F1. Okay, we blow up this point. And then we blow up a next point that is maybe here, or on the -1 curve. We don't care, but we do this elementary transformation, and either we come back to P1 cross P1, or we go to the next Hirzebruch surface. Okay, and here again. And we can do this until we've blown up all the points appearing as base points of F, and at that point we will have done F. And this way, instead of having a surface we don't have control over, we have only Hirzebruch surfaces, and then blow up of Hirzebruch surfaces in one point, which are nice. They are also conic bundles. They have like one singular fiber that is like this. So this is easier to control. So this is what we can do over algebraically closed fields. Now, in general, how do we define it? So, okay. So we define a rank R fibration is a morphism from our X to B. So X is a smooth surface. And the dimension of B is at most 1, so it's a point or a line. The anti-canonical divisor of X is relatively ample. Our map has connected fibers. And the relative pica rank is R. So if I put R equal to 1, I will get back the definition of Mori fiber space. If I put R equal to 2, I will get a Sarkisov link. So in the following sense. So I have F1, the Hirzebruch surface, the blow up of P2 in a point. It has a morphism to P1, B. The anticanonical is relatively ample because it's a conic bundle, literally. Connected fibers, and the relative pica rank is always 1. Sorry, so I should above a point. Above a point. So this is B. This is a pica rank 2. But then I can, so this is the blow up of P2 in a point. This is a Mori fiber space. But I can also see F1 as a P1 bundle. And then here I have a Mori fiber space. And P2 is a Mori fiber space above a point because it's a del beta surface. So what I will do is have this diagram here. So this corresponds, this is F1 blown up in P2, a point blown up in P2. So this is our Sarkisov link. And these are our Mori fiber spaces. I can a different type of circuits of link is I have F1 above P1. I blow up a point on F1. This is a morphism to P1, and the relative picker rank is 2. The relative picker rank is 1. It's a Morey fiber space. And then I contract the strict transform of the fibers. I will get to P1 cross P1 in this case. That also has a morphism to the same P1. And this is a Morey fiber space again. And our circuits of link is actually this one, but I'm saying this is the rank 2. This is the rank 2 fibration. So I have to be a bit more careful. So you can imagine that this is the rank 2 fibration is just one step before the end of the MMP, right? The MMP ends with relative picker rank 1, and then one step before you have relative picker rank 2. And if you have relative picker rank 2, that means your cone of effective curves is of dimension 2. Cone X is 2-dimensional. And it has 2 extremal rays. And those 2 extremal rays, each one gives you a contraction to a Morey fiber space. And the birational map, sorry. X, it's the X, sorry, X over B. Thank you. Yes, thank you. Yeah. Those are the relative cone. So then each gives a birational. This gives the contraction to a Morey fiber space. So we have X over B, and then we go to Z1 over B, and Z2 over B. And basically, and now, okay, so this is picker rank, relative picker rank 2, relative picker rank 1 here. And now we have options. Okay? It's possible that these 2 are birational contractions, and then these 2 are Morey fiber spaces. Okay. So, or this is a birational contraction. This is already a Morey fiber space. Okay. And then we don't really know what this is for the moment. And this is, so we can also say maybe this is a birational contraction, this is a Morey fiber space, this is a Morey fiber space. Okay, so the mirror image of this one. Or last option, both of these are Morey fiber spaces. And the induced birational maps are circuits of links. So here, that's our circuits of link. Here, sorry, this is our circuits of link. For this. And here, the circuits of link is an isomorphism. Well, let me give, so we've seen already examples of this type. So when I have a conic bundle here and here over a curve, and I blow up, I contract the strict transform of the fiber. I could also say this is P2 over a point, some more fiber space. I blow up a point of degree 8, gives me a Bezier surface of degree 1. On it, I can contract exactly one other array, and it gives me again P2 over a point. So this will be a Bertini involution. Okay. That has one single base point, that is of degree 8. Or I could say, the example we saw before, we have P2 over a point. I blow up two Galois conjugate points, and then I contract the line between them, and I go to a quadric surface of picker rank 1. That is also a Mori fiber space over a point. Okay, let me maybe write them down. So this is type 2. P2, go up a point of degree 8, I go to the Bezier surface of degree 1, 2. Or I go up a point of degree 2 and then contract. So, and I go to this quadric that had its rulings exchanged. Which is, so this is a Bezier surface, okay? And the quadric here, that was a form of P1 cross P1, so it's a Bezier surface as well. Then I think, so these two look the same, but I want to make a modification. So here, this was this contraction, but I actually want to say this is the blow up and this is the contraction, sort of. I mean, you can make a difference between them if you want or not. So a priori, this is type 1 and this is type 3. It's just that people look at these diagrams and they see them as directed diagrams and not just as them. So type 1 will be, I blow up a point in F1, and then type 3 will be a contract a -1 curve, the difference. Okay, and then this is the background. So here I have my the Bezier surface, here I have my Mori fiber space, here I have my birational map, and here I just have relative picker rank 1. And the same here. I could also, from the example before, I'll take the quadric I got here in P3, which is the Bezier surface, so Mori fiber space at 1 point. It has picker rank 1. And then I blow up a point of degree 2, as we had in the example before, and I go to a surface that had a conic bundle structure, the Bezier surface of a conic bundle structure. So this one was. Okay. All right, or I could go back to P2 and I pick a point of degree 4. Through 4 points, there is a pencil of conics. And I'll blow up this point of degree 4, and I get to the Bezier surface of degree 5 that has a conic vibration. So basically, I deleted the definition, but the definition forces that whoever is on the top is always a Bezier surface or a conic bundle as well. So this is what makes it easier to control. And then, okay, type 4. Is, for instance, I have two conic bundle structures. And these give me two different Mori fiber spaces. I could say here, I could also say this is, I swapped the two. Sorry. Something like that. But this, so I can do this with any type of, I can also take an empty conic times P1 or two empty conics. Okay, so these are my circuits of links. And the theorem that goes with it was proven by Kotti in 95 and by Skowski in a year later. That says that any birational map between Mori fiber spaces is a composition of circuits of links. This is maybe more of a warning sign that they say they work over any field, but they work over perfect fields. Let me give you two examples of decompositions. Okay, so first, the standard quadratic involution. So, okay, it has base points 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so we start in P2. We blow up a point. We have no option. There is no other link starting from P2. It has no conic bundle structure. And let's say we blow up this point, 1, 0, 0. And we get to F1. And the other 2 points, I will take them with me. Now, F1 over P1. So this is our first link. Now, on F1, I can either go back. The only other thing I can do is blow up one of the other points. So I'll blow up the other points. Now I have to start coloring things. And what I get is if I blow up the point and contract the fiber, my -1 curve becomes a 0 curve, and the 1 curve here becomes a 0 curve, and I go to P1 cross P1. Okay, so I've exhausted already 2 points, and what I can do is exhaust the last point. This one. And I will go back to F1. And then all I can do is go to P2. So here I have a circus of link, a circus of link, and then my last circus of link. So this is a decomposition into circus of link of my standard quadratic map. Okay, now let's look at the other standard quadratic map that we've met, which is the involution at the circle. So it has base points 0, 0, 1, 1, I0, and 1 minus I0. So I have, start again with P2, and I have two options. I can either blow up this point or this orbit. Do you have a preference? I will start the orbit. Very good. So, okay. So these are my 2 points, the line passing through them. So I'll go to the beta surface of dB7 that has 3 curves, and 2 of the curves are exchanged. Remaining -1 curve, which is invariant under the Galois. And I'll go to my quadric, my form of P1 cross P1, whose rulings are exchanged. So this is a link of type 2. Okay, now I'll take my third point with me. Okay, and what I can do now is blow it up. And what I will get is, so I look at the third point is a rational point. There are 2 fibers, geometric fibers through it, that are exchanged, since the point is rational and the fibrations are exchanged. So what I will get is the exceptional divisor of this point, and then, let's say these are the 2 fibers passing, geometric fibers passing through a point. And I'll get 2 5 minus 1 curves that are exchanged by the Galois group. And the only thing I can do is contract these, and I will go back to P2. So I took the third point. It is here. I have a yellow color. Let me maybe color in the point. So this. And then the contraction of the line passing through the pink points is here, and it's somewhere here. So this gives me a second link above. And actually, both Corti and Iskovsky, their proof of their theorem is algorithmic. So there is an algorithm you can follow. If your map is very complicated, it's not so easy to follow, but if you're determined, that's possible. Okay. Now, on 3 vibrations. What are those? They correspond to relations. So the theorem that goes with it is the following. It's I should not write. Space it one. No, that's not the theorem. Sorry, it's not the theorem I want to write down. So I want to cut it into 2 pieces. So that X3 or B3 be a rank 3 vibration. So then we run the MMPs starting from X3. We can run the MMP with respect to the canonical divisor or other divisors, like Cinzia mentioned. And regardless what we do, we only get finitely many outcomes. So they're just outcomes. So there are only finitely many Mori fiber spaces dominated by these rank vibrations. So only finitely many Mori fiber spaces. It's 1 over B1, such that, so if I have my vibration from X3 to B3, and I have some birational contraction to X1, and I get this type of diagram. Because it's possible that B is a point, but then I end in a Mori fiber space above P1. If B3 is a P1, and I run I can run the relative over B3. I run my MMP over B3. So if B3 is a P1, I run my minimum model program over P1. Okay. So moreover, for any Mori fiber space, X1 or B1, dominated by our X3 or 3B, there are at most exactly 2 rank 2 vibrations. X2 or B2 and X2 prime or B2 prime, through which X3 or B3 factors, and in turn which dominates X1 over B1. So what this is saying is that if I have my rank 3 vibration, and I have an MMP that has as output a Mori fiber space, then, so this is rank 3. I have options here. This is rank 1. So I could have that this is relative pico rank 2, so a birational contraction that contracts 2 things, and I can contract these 2 things. I have one contraction, and I have another contraction, and this gives me 2 rank 2 vibrations over B3. Or this is the contraction of one thing, and this has relative pico rank 1. Then this means that this is a point, and this is a P1. So what I will get is my birational contraction to X2. This is my birational contraction to X1. And then here I have pico rank 2. So this is my rank 2 vibration and my rank 1 vibration. So I have, this is my rank 2 vibration, and this is my rank 2 vibration. Okay, so then X3 over B1 and X1 or B2 are rank 2 vibrations. So in order to prove this part, you just play a game with whatever picker ranks are possible, relative picker ranks are possible, and you will always find at most 2 rank 2 vibrations. And now you can lay out these rank 2 vibrations in a circle. So we have X3 over B3, and we have a finite number of Morey fiber spaces that we can get when we start the MMP of X3 over B3. And then in each case, we have 2 rank 2 vibrations. Now here, a rank 2 vibration has exactly 2, a rank 2 vibration dominates exactly 2 Morey fiber spaces. It corresponds to a Sarkisov link, and I can relate it to the next Morey fiber space, and this is a Sarkisov link. Now here, this is X3 over B3 dominating this Morey fiber space. There are exactly 2 rank 2 vibrations between them. I have 1, so there's another one. And then a rank 2 vibration dominates 2 Morey fiber spaces. I get the next one, the next Sarkisov links, and so on. In fact, I can lay them out in a circle, and what I will get is a relation, is a sequence of Sarkisov links that makes a circle like this, and it comes back. Okay, so I have X1, Chi2, Chi3, and so on, and I come back here. And then I will get Chi1 to Chi is an isomorphism of X1, an automorphism. So what this tells you is that rank 3 vibrations correspond to relations among Sarkisov links. This is what we call an elementary vibration, elementary relation. The theorem that goes with it is that actually any relation among Sarkisov links is a composition of these ones and its conjugates. So trivial relations being something like this. So just what I'm saying is that relations between Sarkisov links are generated by elementary transformations. So this is just to be precise. I have, if I have a relation, let's say, and I conjugate by anyone, it is still a relation. Only I don't really care who this is. So it will be some birational map between Morey fiber spaces. Any birational map. So the thing is, maybe they could be this could be an isomorphism a priori. Could be. In that case, you have pick a rank 2, x1, p1, p3. This could be a relation. 1, 1, 1, yes. And a priori in higher dimension, you could have pick a rank 2 here as well, but not in dimension 2. So the thing maybe about relations. So when I have a group and I write the group as with some generators. By set S, and the relations generated by set R. So what does this mean? And I'm not really in group geometry, so we are maybe used to, so I used to learn that I write this like this. I have my generators and my relations. And I don't know, in the case of the symmetric group, you have the transpositions, and then you have some finite number of products. But it's not that what is here are the only relations. You can also compose relations, and you can take, if I have a relation that is here, I can also take any element of G and conjugate the relation with it, and this is also a relation. But I don't need to write it here because this one is enough, this relation is enough to deduce this one. So I just write generating relations. But generating, you need to be maybe a bit precise what is generating, and generating means exactly any relation is a composition of generating relations, is a composition of conjugate of generating relations, and if you want to be very, very careful, you have to add trivial relations as well, because you are writing G as a quotient of a free group. No, free group. You are writing G as words, and you're allowing to cancel letters. And then you have to say that you are also allowed to cancel these letters. Yes, yes, exactly. Yes, exactly. Yeah, yeah, exactly. So this is the free group generated by S, and then the smallest normal. Exactly, yes. Okay, I want to end with one example of an elementary relation. And then in the next course, I will continue with like a recap and examples of elementary relations. And so what we do is we start with P2. Right, so I want to introduce a notation that Julia found to be the most practical one. So if I have a link, so I used to write it like this. This is a Sarkisov link. Or if you want, you have and then you can choose. So this is the rank 2 vibration. These are the circuits of link. These are the Moore fiber spaces, and then you choose which ones are of rank 1 or 0. For writing down the relations was actually the best way was to write it on a line like this. I have here at the edges my Moore fiber spaces, and then in the middle my rank 2 vibration. That gives me the two contractions. Well, we started off with sort of this one. It was not practical. I went to this one. It gives sort of funny pictures, and then Julia started with this one. It gives very symmetric pictures. So. Yes, but only because we have a list of all the possibilities. Yeah, it's. I think I'm not quite sure whether. So I think in dimension 2 you can find a bound abstractly without going through the list, because in the middle the rank 3 vibration is a Del Bezzo surface or a conic vibration with something, but then in higher dimension I think that's more difficult. Yeah. Okay, so I will start with P2, and in P2 I want to blow up two rational points. Okay, so I blow up a point of degree 1 and another point of degree 1. And in each case, remember, so I go to F1, and F1, the link diagram is the following. So this is my P1, I blow up a point, and I get the rank 2 vibration is F1 over a point, and then the Moore fiber space is P1. So I can write here F1 over a point, and then here F1 over P1. And then if I blow up a second point, I get the same picture. Now, I blow up two different points. I can blow them up in any order. Maybe I'll color in. Which ones they are. And I will get to my rank 3 vibration. And the rank 3 vibration is, so P2, rank 1, rank 2, rank 3 is over a point. Now, the structure, the P1 bundle of F1 lifts to the 1 on X3. Okay. And this structure lifts also to X3. Now, I can blow up the red point on F1 as a Del Bezzo surface or as a conic bundle. Okay, this is the blow up. And if I blow up a point on a conic bundle, I can contract the strict transform of the fiber. And this gets me to P1 plus P1 or P1. Okay, so this is my. This link. No, I'm sorry. F1 and then P1 plus P1. Okay, and I can do the same here. I can blow up the blue point on my P1 of my bundle, and I contract the strict transform of the fiber, and I get to P1 plus P1 of P1. And now what? Actually, what I've done is, so by blowing up 2 points, I go both ways to P1 cross P1, but the vibration is the one corresponding to each point. So here, these vibrations are not the same. This is maybe the vibration for the first projection, this is the one for the second projection. And what relates them is the exchange of the 2 projections. The exchange of the 2 projections was P1 plus P1. Yes, this type of link. So here the rank 2 vibration was P1 cross P1 over a point. Okay. So this is my elementary relation. What I'm saying is that I can blow up a point, blow up two different points. Both these blow-ups will lead me to P1 plus P1, but with the 2 different vibrations, and then when I exchange the vibrations, I will go full circle. Okay. So, or in other words, I blow up a point on P2, go to F1, I blow up another one, contract the strict transform, or go to P1 cross P1. I exchange the vibrations, and then I go back, and I arrive from P2. Go back to P2. Okay. I will leave it like this. I will do a second example in the next lecture.